Okay, so this is the review session for EGME 407 for midterm 2 for spring 2022. Okay, so I looked at the poll online, and these were the two winning topics. So internal convection won by quite a significant margin, and number 2 was heat exchangers. So that's going to be the topics for the review session for today. Okay, so let's go ahead and get started. All right, so let's go over heat internal convection, and it's kind of nice because these two topics are related to each other. Internal convection being kind of the you can almost think of it as like the prelude or the precursor to heat exchangers. Okay, so when we're talking about internal convection, what we're talking about is the heat transfer to a flowing fluid that's inside some kind of flowing device. So most of the time, it's going to be a pipe. Okay. Okay. And so just like I mentioned, the stereotypical case for this is flow inside of a tube or a pipe, right? And so visually, we look at it as something like this, right? And so we look at kind of a cross section of the pipe, okay, where the fluid is flowing in between the walls of the pipe. Okay. Okay. Something like that, right? So there's kind of a lot of information, that's there in the notes. A lot of it has to do with fluid mechanics and has to do with thermal, right? But I think that the most important thing that I want you to remember with internal flow is that, generally speaking, because there's a finite amount of fluid inside this pipe, any heat transfer to or from this fluid is going to affect, the thermal state of that fluid. Okay. And so what do I mean by that? And so what I mean is that, if you have heat transfer that's coming into the pipe, okay, and so in this case, we're going to say that the fluid inside the pipe is being heated, okay. Normally, when we talk about convection, and when I say normally, I say, before we started talking about internal convection, whenever we had heat transfer to a fluid like this, the fluid was kind of unaffected. And so it's what I mean by that is that, we assumed that the temperature of the fluid did not change. Okay. For internal flow, this is not the case because we have such a confined space where the fluid is flowing, the temperature of the fluid is going to change. And so what this statement at the bottom here, what that's basically saying is that the temperature is going to change. And the way that we quantify this, and the way that we, the way that we, talk about this is by quantifying the mean temperature of the fluid as a function of Z. Okay. Okay, where Z here is our axial coordinate. So that's the coordinate that goes down the length of the pipe, right? And so this direction here, that's the z direction. Okay. And so the mindset with internal convection changes a little bit, right? And so if you compare it, compare it to like external convection and free convection, internal convection is a little bit of an odd one out, okay? Because not only do we have to worry about computing the convection coefficients, we also have to worry about computing what this mean temperature is, okay? And so we have two formulas for this, right? And so we have basically two scenarios where we can compute this mean temperature, because how the mean temperature evolves as a function of z depends on what's happening around it. Okay. So let's go ahead and split this up into two. And so the first case that we went over in the class is the case when the heat flux into the pipe is constant. Okay. And so visually it looks something like this. And so we have a pipe that's like this. Okay. And the heat flux refers to the flow of energy going into the pipe, per unit area. And so if we quantify, maybe I shouldn't have kept using red. I'll use pink. Okay. And so constant heat flux, all that means is that the amount of heat or the amount of energy that's coming in, it's constant throughout this entire pipe. Okay. And so what we can say is that Q naught double prime constant along the whole pipe. Okay. And so under those conditions, what we say is that, as the fluid flows, and so, we're going to say that the fluid is going to start at a temperature Ti here, right? And so as the fluid flows, and so as it goes from left to right here, then it's going to gain energy, from the heat flux that's coming in, right? And so for now, we'll assume that the heat flux is going into the pipe, okay? Okay. And so, every inch that the fluid goes through, it's going to gain, that amount of energy. And so that's the same, from the beginning to the end, because what we say is the heat flux is constant. Okay. And so if the fluid is gaining a consistent amount of energy, then what we say is that what we can say is that the mean temperature of the fluid is also going to climb steadily as well. Right? Okay. And so if the mean temperature is going to climb steadily, then mathematically we can represent this with a linear function, right? So the linear function grows at a steady constant slope as you go from one end to the other. Okay. And so the formula that we had in the lectures, we had Tm of z. Okay. This is equal to our heat flux, right? So that's the heat flux that's coming through the wall times the perimeter divided by the mass flow rate times the thermal capacity times z plus Tmi, where Tmi is the mean temperature of the fluid at the inlet of the pipe, or wherever the beginning of the pipe that you're considering. Okay. Okay, and so you can see here the only z dependence that we have here is on the first term, which is a linear function. Okay. And so this is the expression of what you would have if the fluid was gaining heat. Okay. But of course, we also have situations where the fluid will lose heat as well, right? And so I think we had a homework problem about that, with the air conditioning, right? And so the way that we can account for that is by just simply making the heat flux negative, right? Because if the fluid's gaining heat, we expect the temperature to increase as we flow along the pipe. But of course, if the fluid is losing heat, or if the heat flux is going out of the pipe, and we expect the heat flux to, the temperature to decrease. Right? And so we can simply do that by just changing the sign of this Q naught. Okay. All right, so that's the constant heat flux case. And so for constant heat flux, we have a steady climb of temperature. The other situation that we went over was constant surface temperature. Okay. Okay. And so constant surface temperature, let me go ahead and draw it schematically. And so when I say surface temperature, what I'm referring to is the temperature of the walls inside the pipe, right? And so, if we measure the temperature here, we call this TS, right? This TS is going to be the same all throughout the entire pipe. Okay. Okay. All right. And so if TS is constant throughout this entire pipe, if it's going to be different than TM, the mean temperature, then of course heat transfer is going to occur, right? Okay. In other words, if the surface temperature is different than the fluid temperature, then of course, we know anytime that there's a temperature difference, or there's going to be heat that's going to be flowing. Okay. But because the surface temperature is constant, right? And so you can imagine that as kind of like a horizontal line. So I think this is best kind of illustrated as a plot, right? And so if we call the x-axis here, we call that z, I guess. Okay? And if we quantify the constant surface temperature as something like this, okay, right? So it's going to be constant throughout the entire pipe. Of course, we might have a situation, and we'll assume here that the fluid again is being heated up, and so we'll assume that the fluid temperature starts down here, right? So we'll call this TMI, for the inlet temperature. Right? And so since there's this gap in between the two, TM is going to go up, right? Maybe that's not it's not too accurate. Let's say it looks more like this. Okay. Right. So TM is going to increase because it's being heated by the wall. But notice how it doesn't go up at a constant rate, right? So at first, we have a very rapid increase, right? And so you can see here the slope of this line is pretty intense. But then as we flow, as TM approaches TS, then that increase for TM slows down quite a bit, okay? And so the difference here is that, remember, heat transfer, the bigger your temperature difference between two things, the greater the amount of heat transfer there's going to be. And so at the beginning here, we have a lot of heat transfer because our delta T, right, so we call this delta T, our delta T is very big here. And so that's going to lead to a large amount of heat transfer. But then as TM creeps up and creeps up, then that delta T is going to decrease, right? And so if we measure delta T right here, right, that of course is going to be a lot smaller than the delta T at the beginning. And so if delta T is smaller, that means Q is going to get smaller as well. Okay? And so what we can say is that delta T shrinks okay. Delta T is going to shrink along the length of the pipe, and therefore the heat transfer is going to shrink along the length of the pipe as well. or excuse me, therefore Q is going to shrink along the edge of the pipe. Delta T is going to shrink, therefore delta T is going to shrink. Yeah, great, excellent logic there. Okay. And if Q is going to shrink, that means the rate at which Tm is going to increase is also going to decrease as well, right? And so the way that we mathematically represent this is through a decaying exponential function, okay? And so the expression that we had in the class was the following, right? So we had Tm of Z is equal to Tmi minus the surface temperature, Ts, times exponential of minus P. Oh, if I didn't mention before, P is the perimeter, okay? Multiplied by H, so H here is the convection coefficient, and so that's new, and so we don't have that there. But because we're basing this off a temperature difference, then the convection coefficient has to be there in order to characterize the amount of heat transfer that occurs. Okay. We divide this by m dot Cp multiplied by Z, okay, plus Ts, the surface temperature. Okay, so here's our Tm, right? And so mathematically it looks very different than our constant heat flux case, right? Okay, and so if I zoom out a bit, it's a little bit too much. Okay. Here are our two cases, right? And so I wanted to talk about this in detail because this is something that really sets internal convection apart. And convection and conceptually, it's really important to understand, in terms of what's happening with internal convection. Okay. And so, just remember that, when we're considering, free convection, external convection, the mean temperature or the fluid temperature there is not going to change. But most of the time, with internal convection, the fluid temperature is going to change, and that has to factor into your analysis, in some way or another. Okay. Okay. All right. So that's the mean temperature, right? So I'd say that's kind of conceptually speaking, that's the most important thing to take away from internal convection. Let's talk about convection coefficient, right? And in particular, let's talk neutral correlations. Okay. And so we have two groups of neutral correlations here, and again they're going to depend on whether the flow is laminar or the flow is turbulent. Okay. Okay. And so the first thing you should know about computing convection coefficients in internal flows is what is that cutoff, right? And so, remember the way that we determine whether a flow is laminar or turbulent is we compute the Reynolds number, okay? And so for internal flows, the Reynolds number is the mean velocity multiplied by the diameter divided by the kinematic viscosity, okay? Where a lot of times you're going to have to compute the mean velocity based on either the volumetric flow rate or the mass flow rate, okay? Okay. And so it looks something like this, right? And so if you're given the mass flow rate, the mean velocity is going to be the mass flow rate, m dot, divided by rho, multiplied by the cross-sectional area, right? So the cross-sectional area most of the time is going to be the area of a circle, if we have circular pipes, which we do most of the time, okay? Or if you're given volumetric flow rate, so volumetric flow rate will be something like meters cubed per second, milliliters per second, okay? The way you compute, and so the symbol we usually give that is usually q dot. And so the way we compute mean velocity is q dot divided by the cross-sectional area, okay? And so most of the time for internal flows, you're not going to be given the mean velocity straight up. And so it's important to determine the mean velocity from what you're given in the problem, okay? Okay, and then everything else in this expression is pretty self-explanatory. So we have the diameter, so that's usually given to you, as well as the viscosity, which you would look up in a table, but for the exam, it's going to be given to you. Okay, and so we have two regimes here, and so the magic number for internal flow is 2300, and so if our Reynolds number is less than 2300, okay, then we have laminar flow. But if our Reynolds number is greater than 2300, then this constitutes as turbulent flow. Okay. Right. And so, you guys have been doing this, for a while now. And so, you know that whenever you have convection, Reynolds number is always something that you have to, that we have to attain. Okay. And then from there, you make a decision on what Nusselt correlation that you want to use. Okay. Okay, so let's go over the laminar case first. All right, so for a laminar case, we have two different options here. And so we have or two different cases, I should say. Okay. And so we can either have Nusselt number is equal to 4.36. Okay, so it's just a constant, and so there's no formula for this. Okay, or we can have Nusselt number is equal to 3.66. Okay, and 4.36, this is for the case when we have a constant heat flux. Okay, and 3.66, this is for the case when we have constant surface temperature. Okay, so that's the laminar case. Let's go over the turbulent case now. Okay, so for turbulent flow, we have kind of a regular looking Nusselt correlation for this. Okay? And so for turbulence, it doesn't really matter if you have constant heat flux or constant surface temperature. They're both kind of the same. Okay? And so what we have instead is we have Nusselt number is equal to 0.023 times the Reynolds number to the 4/5 times Prandtl number to the n. Okay, where n has two possible values. So n is equal to 0.4 if the fluid inside the pipe is being heated. Or we have n is equal to 0.3 if the fluid in the pipe is being cooled. Okay, and so that's the Nusselt correlation that you would use if you had turbulent flow, for internal flow. Okay. Okay, and so I know there's a lot of information in the internal convection notes, but I'd say these are the most important ones that I want you to know. Okay. Okay, and so normally at this time I would do an example to show what's important for this, but because internal convection and heat exchanger are so closely related, I'm going to hold off on that. Okay, and in fact at the end I plan on doing an example from a previous exam, actually from an exam I gave 3 years ago, that covers both. Okay. Okay. All right. And so let's go ahead and move on to heat exchangers. And so heat exchangers, is a very unique unit because it's it's very similar to our discussion on fins, where physically speaking, or from a physics point of view, we're not covering anything new here. And so heat exchangers are basically, you can almost think of it as like an applied application or an applied example of internal flow. Okay. Okay. And in fact, actually, right before I was making this video, the water heater in my apartment is kind of on the fritz, and so my wife has been asking me to look at it, and so I was watching videos on how a water heater works. I'm like, hey, that's a heat exchanger, and that's internal convection, right? So that's very very fitting. Okay, so everyone has a water heater in their home, and so that's a prime example. And so the idea with heat exchangers is that you have two fluids that are running right next to each other. Okay. And so here I'm just doing a very simple case. And so we have fluid 1, fluid 2. Okay. And usually there's a strong enough temperature difference between these two fluids in order to cause heat transfer to occur between them. Okay. And so we might have heat transfer that goes this way. Okay. And so on and so forth. Okay. Okay, so that's the basic idea. And so the basic idea with heat exchangers is that you have two fluids, one that needs to be heated up and one that needs to be cooled down. Or maybe you just need to do one, and so maybe you just need to cool off one fluid, and the other fluid is just there to act as a coolant. Okay, but anyway, you have two fluids, and they're going to exchange heat, and a heat exchanger is designed to make that process as easy as possible. Okay. Okay. And so this is kind of the simplest drawing of one, but it's not the case that we actually use in practice. And so the one that we actually analyze for the class is a concentric tube heat exchanger. Okay. Okay. And I bring this up because a lot of times when you look at a figure for a heat exchanger, you're going to see three flows, right? And so you're going to have something that looks like this, okay? And so it looks like you have 3 channels here, which is different than the top figure where you only have 2, right? But what these 3 channels represent is that you have kind of a smaller tube inside a bigger tube. And so if you slice it kind of halfway, the outer fluid is going to surround the inner one. Okay, so here we have fluid 1. Okay, fluid 1. Okay, and so that's we call that the outer flow. And inside we have the other fluid, so fluid 2. Okay. Okay. And so one important formula, before I kind of get too deep into the weeds of parallel flow, counterflow, is to know how to compute the amount of heat transfer in just one fluid. Okay. Okay. And just like we talked about previously, right? So just like we finished talking about internal convection, when you give heat or you take heat away from internal flow, it's going to cause a change in the fluid temperature, right? And we can use that difference in the fluid temperature, or the amount of change in fluid temperature that occurs in the heat exchanger, to characterize the amount of heat that gets moved into and out of the fluid. Okay. And so the formula is the following. And so we have Q is equal to m dot, which is the mass flow rate of the fluid going into that particular pipe, okay, times Cp, which is the thermal capacity of that fluid, multiplied by the difference between the inlet temperature and the outlet temperature. Okay. And so recognize that this is just for one fluid, right? So remember, in heat exchangers, you have two fluids. And so, if you're just looking at a single fluid, this is the amount of heat transfer that occurs within that one fluid. Okay. And so when I say inlet and outlet temperatures, you have to be careful here that you're using the same fluid for them. Okay. Okay, so don't mix them up. Okay. Okay. And so I think that's probably one important formula to know from this. Okay. So that formula, we can actually derive that from the internal flow that we had before. It's kind of important here for heat exchangers. Okay. All right, and so to that end, there are two, there are two types of heat exchange, or two types of flow geometries that we can consider, and they have very different properties. Okay, and so let's go over the first one we went over, which is called the parallel flow heat exchangers. Okay, and so the idea with parallel flow heat exchangers is that the fluids are going to run in the same direction as each other. Okay. Okay. Another way that you can put this, and I think this is probably more useful in terms of your calculations, is that when the two fluids are flowing in the same direction, that means their inlets are right next to each other. And so the inlets occur at the same place in the heat exchanger. Okay. And so schematically, it looks like this. And so I'll draw the version with the concentric tube heat exchanger. Okay. All right, so just like before, we have fluid 1 on the outside, and we have fluid 2 on the inside. Okay. And so in parallel flow, these two are going to be flowing in the same direction. Okay. And so we have flow going from left to right. Okay. And so since they're flowing from left to right, that means the inlets are going to be on the left. And so we have T1 inlet, T1 inlet. Okay. And the inlet for fluid 2 is going to be on the left as well. Okay. T2 inlet. And of course, if their inlets are in the right place or in the same place, that means their outlets are going to be in the same place as well. And so we have T1 outlet, T2 outlet, and T1 outlet. Okay. Okay. And so the important thing to know, about both geometries of heat exchangers is that is how the temperature profile develops within the heat exchanger. Okay, so we drew these plots in the class. Okay, but that's kind of the big difference in between the two. Okay. Okay, and so we have something that looks like this. Okay. Okay, so let's do the hot fluid first. And so, we'll say that, one of these is hot. Okay. All right, so the hot fluid is going to come in, it's going to be really, really hot. Okay. But through interacting with the other fluid, the temperature of the hot fluid is going to decrease. Okay, and so it's going to go down just like that. Meanwhile, the cold fluid is going to come in really cold, and then by interacting with the hot fluid, it's going to heat up. Okay, and so it's going to come up just like that. Okay. And so what do we notice here? And so what we notice right away is that initially we have a very large delta T, right? And so this delta T here is very large. Okay. Just like we talked about, 15 minutes ago with internal flow, right? The greater your delta T, the greater amount of heat transfer that occurs, right? And so at the very beginning of a parallel flow, you have a lot of heat transfer that's occurring, because of the temperature difference. Okay. But as the two fluids exchange heat, they're going to come closer together in terms of temperature, right? That's generally what happens when you have two objects that are different temperatures, right? So because they want to attain thermal equilibrium, right? And so that's exactly what you see here as the two fluid temperatures come closer and closer together, right? And so as you get closer over here, delta T is a lot smaller. And so because of this, we have this interesting trend where, at the beginning or near the inlet of a parallel flow, you have a large amount of heat transfer. Okay. Okay. But then that quickly diminishes. And so as you kind of flow along and the fluids get closer in temperature, that Q is going to diminish. Okay? Okay. All right, and so the other type of heat exchanger that we have is a counterflow heat exchanger. Okay. And so in these situations, we have the flow of the two fluids is in opposite directions. Okay. So visually it looks like this. And so here we have our concentric tube heat exchanger. Okay. Okay, so let's say that fluid 1 flows from left to right. It doesn't really matter, but we have to choose a direction here. And so fluid 2 is going to go from right to left. Okay, so that's what it looks like visually, but in terms of your calculations or in terms of how you analyze this, the upshot of this is that the inlets for the two fluids are on opposite sides of the heat exchanger. Okay? Okay. And so that means the inlet of one fluid is going to be matched up with the outlet of the other one. Okay. Okay, so let's go ahead and draw this visually just so you can see what it looks like. Okay. Okay. And so again, we'll assume that fluid 1 is the hot temperature. Okay. get the hot fluid, and so the hot fluid is going to come in really hot, right? And so we'll say that's coming in from the left, but the cold fluid is going to come in from the right. Okay, and it's going to start down way down there. Okay. And as we understand it, as the fluid flows through the heat exchanger, the temperature of the hot fluid is going to go down, right? And so it's going to go down just like that. Okay. Meanwhile, the temperature of the cold fluid will go up, and so it's going to go up just like that. Okay. The difference here, compared to our parallel flow, is that if you look at the delta T, between them, delta T is pretty consistent. Okay, and so if delta T is pretty consistent, that means that the amount of heat flux, or the amount of heat that gets transferred between the fluids, is almost constant throughout the entire heat exchanger. Okay. Okay. All right, and so that's the difference. And so, if you were to kind of put this in practical terms, right? So the question is, when is it better to use a parallel flow? When is it better to use counterflow, right? And so generally speaking, the counterflow heat exchangers are best when you have a lot of operating space, right? And so if you can have a lot of real estate, or you have long lengths that you can make your heat exchanger, counterflow is always going to be more valuable, because as you get into the higher and higher lengths, as you make the heat exchanger longer and longer, you still gain some value out of that, and so you still gain some heat transfer from that. Okay. For parallel flow, that's not necessarily the case. So for parallel flow, it's great in the beginning, but as you make it longer and longer, it's not as effective. So you don't get as much value out of making a longer heat exchanger. Okay. But with that said, if you only have a short amount of space, which is very common in these kinds of devices, then a parallel flow heat exchanger will give you better performance, because it kind of maximizes that heat transfer at the beginning. Okay. Okay. All right. So what else we have here? Okay. So we are running a bit out of time, and so because I do want to go over an example. Okay. But I do want to talk about the concept of effectiveness before we do that. Okay. And so effectiveness is basically a metric, or it's basically a way for us to quantify how well a heat exchanger is performing. Okay. Okay. And so the way that we do this is we compute this effectiveness, and this effectiveness represents a ratio. Okay. And so the effectiveness, we give it the symbol epsilon. Okay. And so we say that it's the ratio of the actual amount of heat transfer that gets in a heat exchanger, okay, divided by the maximum possible heat transfer. Right? So it's kind of like life a little bit, right? So you're always kind of compared to perfection, or what people deem as the ideal, the ideal representation of a certain thing. Okay. And so let's talk about, this. I think epsilon, there's ways that we compute it, right? And so we have an expression for parallel flow and counterflow. But I want to talk a bit more about what this kind of conceptually means. In particular, I want to talk about the denominator. Okay? Okay. And so what I mean, and so when I talk about the maximum amount of heat transfer that occurs in a heat exchanger, what I mean by that is this is the max amount of heat transfer that occurs for these two fluids. Okay. Because when two fluids are coming in, there's only a certain amount of heat transfer that can occur between them, before it's capped, right? Because if you talk about the max amount of heat transfer that can occur ever in the world, that's going to be infinite, right? And so when I say the maximum heat transfer, what I mean is what's the maximum amount of heat transfer between these two fluids, right? Because the two fluids are going to come in, and so what's the max amount of heat that they can exchange throughout this device? Okay. Okay. And so I'll give you kind of an extreme case. And so if you have two fluids that are coming in and they're coming in with the exact same temperature, then it doesn't matter, you could be the best thermal engineer in the world, right? You're not going to get those two fluids to exchange heat between each other, right? Because they're already the same temperature. And so, when I talk about the maximum amount of heat transfer, that means for these particular fluids. Okay? And so conceptually, if you have two fluids and they're at different temperatures, they can achieve the max amount of heat transfer when basically the two fluids, can reach each other's temperatures, right? Or maybe I'll put this in a different way. So the max amount of heat transfer occurs when you have a maximum amount of temperature difference between the inlet and outlet of a fluid. Okay? Okay. And so I think visually, it's always good to draw this kind of visually, right? All right. And so, whenever you have two fluids coming into a heat exchanger, it's always, the temperature difference or the temperature change is always going to be bounded, okay? Right, because you have hot fluid that's going to come in, right? And you have cold fluid that's going to come in, okay? And so these inlet temperatures, the inlet temperatures between the difference in temperature between your inlets, that's going to be the bounds, right? And so there's no way physically possible for the temperatures of any fluids to exceed these two bounds. Okay. And so these you can kind of think of them as kind of like bounding lines for the entire heat exchanger. Okay. And so the most possible heat exchange that can occur is so that if the hot fluid is given enough time to cool all the way down to the cold fluid inlet, okay. And meanwhile, and for the cold fluid, that means that's going to heat up all the way until it reaches the hot fluid temperature, okay. Right. And so that represents the best case scenario, or the maximum amount of heat that can be transferred between these two fluids, okay. And so what kind of geometry is that occurring? Well, I kind of given that away here by the figure, but this can only occur in a counterflow heat exchanger. Okay. It can only occur in a counterflow heat exchanger where the length of this heat exchanger is infinite. Okay. And so basically the fluid has an infinite amount of time for it to gain a temperature. Okay. And so the way that we can quantify this, and so we'll call this Q max, okay? Q max is going to be m dot Cp, but it's going to be the minimum, okay? Because that's going to be limited by, you know, whichever m dot Cp is lower between the two fluids, okay? Multiplied by the difference in between the inlet temperatures. Okay, so we have Thi minus Tci. Okay. Right, so that's the max amount of heat transfer that you can get, you know, from a heat exchanger. Okay. Okay. All right. And so with that, you know, I do want to do an example. I don't have that much time, but you know, we'll try to go through this really quickly. Okay. And so this example here will be kind of a good combination between heat exchangers and you know, an internal flow. Okay. And that example is, you know, we're just going to be looking at a heat exchanger. Okay. Okay. And so let's consider a situation where hot water is going to be cooled by air. Okay. Okay. And it's going to happen in a counterflow heat exchanger. Okay. All right, so visually it looks something like this. Okay, and so we're going to say that the hot water is going to flow on the outside. Okay, the air is going to flow on the inside. Okay, and we'll say the water is going to go from left to right, and the air is going to go from right to left. Okay. Okay. And so what we're going to assume is that the inner diameter here is di, and the outer diameter do. Okay, so we're going to say that di is equal to 2 centimeters, do is equal to 5 centimeters. Okay. We'll assume that the wall that separates the air and the water has negligible resistance. So there's no, you know, there's no thickness there. Okay. So, you know, even if there is, we're going to ignore it. The mass flow rate, so the mass flow rate of the air is going to be 0.35 kilograms per second. Okay. Meanwhile, the mass flow rate of the water is going to be 0.3 kilograms per second. Okay. And here we're given the inlet temperatures of both fluids, and so we'll say that inlet temperature of the air inlet temperature is going to be room temperature, 25 degrees C. The inlet temperature of the water is going to be 75 degrees C, so fairly hot. Okay. Okay. And in this particular problem, we're actually given the outlet temperature of the water as well, and so we're going to say that we want to design this heat exchanger so that you know, we achieve an outlet temperature of 60 degrees C. Okay. Okay. Right, and of course, you know, we need our fluid properties, and so you know, for this, and so this is a good example of what can happen on the exam, and so you know, for these ones, I would just give you the fluid properties just kind of straight up. Okay. So we have two fluids, air and water. Okay. Okay. And so we have the density. We have the thermal capacity. Let me just draw the symbols actually. Okay, so we have the density, we have the thermal capacity, that's Cp. We have the kinematic viscosity, nu. We have the thermal conductivity, and we have the Reynolds number. Okay, so the density for air is 0.995 kilograms per meter cube. Okay, the density of water we'll assume is 998 kilograms per meter cubed. Okay, Cp for the air is 1009 joules per kilogram K. CP for the water is 4181 joules per kilogram K. Okay. Kinematic viscosity is 20.92 times 10 to the minus 6 meters square second. And for water, it's going to be 9.61 times 10 to the minus 4 meters square second. Okay. Thermal conductivity for the air, it's going to be 0.03 watts per meter K. And for the water, it's going to be 0.606 watts per meter K. Okay. Reynolds number for the air is going to be 0.7. For the water is going to be 6.62. Okay. Okay, and so part A of this problem. In part A of this problem, let's compute, the total amount of heat transfer that needs to occur in this heat exchanger. Okay. All right, and so luckily in this problem, we are given the outlet temperatures of the fluid, right? And so if we're given both the inlet and the outlet temperatures, we can compute the heat from that. Okay, and so Q total here is equal to m dot Cp of the water multiplied by the inlet temperature of the water minus the outlet temperature of the water. Okay. Right, and so this is just a simple plug and chug, and so we have m dot for the water is 0.3. Okay, Cp for the water is 4181. And we have an inlet temperature of 75 and an outlet temperature of 60. And so the difference is 15. And so you plug in all the numbers for this, and you get a total amount of heat transfer of 18,814.5 watts. Okay, so that's part A of the problem. Okay. So that's kind of the heat exchanger part of this problem. And so part B is going to ask us to compute the convection coefficients of both flows. Okay. Okay. All right, and so for this, of course, we have, our process for this. Okay. And so luckily for us, we've already been given, we know the flow geometries here, right? So we have flow in an annulus for the water, and we have flow of air, a flow in an internal tube for the air, okay? The properties were given to us, and so we can just read it off there. And so the next part is just to compute the Reynolds number. Okay, so we're gonna start with that. Okay. And so I'm going to do this in two quantities, right? So let's do for the water first. Okay. And so for the water, our mean velocity here is going to be, or excuse me, our Reynolds number. Let's start with that first. Okay. And so our Reynolds number, remember the water here is flowing in the annulus, right? Remember for the annulus, we have to use different rules for that. And so the Reynolds number for an annulus is the mean velocity multiplied by the hydraulic diameter divided by nu. Okay. Remember, hydraulic diameter here is just the difference in diameters of the annulus, and so we have dO minus di. Okay. And the mean velocity we're going to compute based off the mass flow rate, and so we have m dot divided by rho AC. Okay. Where m dot's given to us in the problem. The density is also given to us, it's 998, okay? But AC here, AC is just going to be the cross-sectional area of that annulus. So it's going to be pi divided by 4 times dO squared minus di squared. Okay. And so we end up with the mean velocity of, oops. We end up with a mean velocity of 0.182 meters per second. Okay. And so if we compute the Reynolds number, from this, we get 5.689. We'll just round up 5.69. Okay. Okay. And so of course, this is a very small Reynolds number, and so this means our flow here is laminar. Okay. Okay. And so that's the water, and so that's our situation for the water there. Okay. For the air, we have flow in a pipe. Okay, and so for the air, we're going to do UM is equal to m dot of the air divided by rho. And here, since we just have a pipe, we're going to have d pi over 4 di squared. Okay. Right, and so we end up with a very big number here because the m dot's pretty big and the area is small, and so is the density. And so we end up with 1119.7 meters per second. Okay. And so if we compute the Reynolds number for this, and so the Reynolds number for internal flow is UM times the diameter divided by nu. Okay. And so we go ahead and plug the numbers for this, we get 1070442.66. Okay. And so since this is much greater than 2300, this is turbulent. And in fact, it's omega turbulent. Okay. Okay. All right. So next step is to compute the Nusselt numbers. Okay. And so for the water, since we have laminar flow, we need to use a Nusselt correlation for an annulus. Okay. So let me go ahead and look it up. I don't have it in front of me. Okay. Right. And so in order to compute the Nusselt number for an annulus, okay. If the flow is laminar, then we simply just take the ratio of di over do. Okay. And then what you do with that ratio is that you compare this to table 8.2 in the book. And what that table shows you is that, for certain ratios of di over do, that's going to give you different values for the Nusselt number. Okay. And so for this particular one, with a di over do, and so we go ahead and compute that. Okay. And so di over do, this is 2 centimeters divided by 5 centimeters. Okay. And so that gives you a di over do of 0.4. Okay. And so you're going to look up in the table for an entry for 0.4. Okay. And unfortunately, in the table, there is no entry for 0.4. And so you're going to have to interpolate for a bit. Okay. And so for this particular one, if you interpolate, you end up with a Nusselt number of around 6.5. Okay. Around there. Okay. Okay. All right, and so that's for that one. Okay. For the air, since we have turbulent flow, okay. For the air, what we're going to do is we're going to use our turbulent flow Nusselt correlation. Okay, so we have Nusselt number is equal to 0.023 Reynolds number to the 4/5 times Prandtl number Prandtl number is raised to the n power, but here, since the air is being heated up, we're going to raise it to the 0.4 power. Okay. Okay, because the air is being heated up. Okay. And so we compute that. We go ahead and plug it in. We get a Nusselt number of 1328.67. Okay. And then after we do that, now that we have the Nusselt number, computing the convection coefficients is very easy. And so what we do here is we do H is equal to Nusselt number times thermal conductivity divided by for the water, which is an annulus. Okay, we're going to divide this by the hydraulic diameter. Okay. And so if we take our Nusselt number of 6.5, we multiply by the thermal conductivity, which is 0.606, and we divide by the hydraulic diameter, which is 0.03. Okay. We end up with a convection coefficient of 131.3 watts per meter squared Kelvin. Okay. For the air, we have H is equal to Nusselt number times the thermal conductivity of air divided by the internal diameter, okay, DI. And so we plug this in and we get 1993 watts per meter squared Kelvin. Okay. Okay, so that was a good example because we had a little bit of heat exchanger methodology here, computing the heat transfer, but we also had we went through and we did a bit of practice of doing our convection problem solving methodology. Okay. Okay, and so that's all the time I have for this review video, and so hopefully it's useful to you guys. Okay, so of course there wasn't time to cover absolutely everything with especially with heat exchangers, and so make sure you're reviewing the study guide and you're reviewing the notes for that. Okay, and if you have any other questions on anything, please don't hesitate to let me know. Okay, all right, so best of luck studying to everyone, and I will see you all. And depending on when you see this, I'll see you all in class. Okay.